Hello, and welcome to a basic intro to reverse engineering video games with Ghidra. Ghidra is one of the most powerful tools that a video game hacker has under their belt, and we're going to be going through some of the just basics on how to get it working and how to use it in your projects for decompiling and modifying game behavior. This is quite an advanced topic. This is not an introduction to hacking games in general. This is really just an introduction to Ghidra itself. There's a lot that you should already know when it comes to programming, such as the C programming language, at least some flavor of assembly code. You should know how the C compiler and linker actually works to produce an executable binary, because that's what you're going to be really dealing with in Ghidra. You should know about how data formats work, because that's something that you'll also encounter in Ghidra, is how to deal with data as well as code. And you should also know the quirks of whatever platform it is that you're working on, such as the PS1 or the Game Boy or whatever it is, because each platform will have different quirks and different little things about it that you have to be aware of when you're messing around with it in Ghidra. So what does Ghidra even do? Well, it's a program for disassembling code. That's something that it does automatically, but that's something that a lot of other programs can do. What makes Ghidra really special is that it decompiles code automatically and allows you to add your own symbols to make that automatically decompiled code resemble something that's pretty close to source code. You can identify different pieces of data, like strings or structs, and have that embedded in the code itself. You can also use different extensions to link symbols from whatever SDK for whatever platform you're using, like the PlayStation 1. And it could probably do a lot more stuff that I don't even know about because I haven't been using it for that long myself. But more to the point, what Ghidra really does is it makes it easier to understand and modify game behavior on a very much deeper level, something approaching what the original designers were intending. And then in combination with an assembler, you can modify that code after you have finished understanding it. The only limitation to what you can do with these two tools is how much time you're willing to invest, because otherwise the possibilities are endless. So let's start with installing Ghidra. A lot of people seem to think that it's a complicated process where you have to install Eclipse and compile it from Java. No, you don't need to do any of that. You can just grab the zip file from GitHub and you're pretty much just ready to go after unzipping it. It'll just run after unzipping. The first thing that you're going to want to do after installing and running Ghidra is to install your extension for whatever platform it is you're targeting. So just hit File, Install Extensions, then hit that little plus, and then select whatever zip package you got as the extension itself. This will do a lot of things for you that make it a lot easier to deal with the platform, but you'll see that later. So what do these extensions actually do? Well, it automates a whole bunch of stuff that would otherwise have to be done manually. For example, for the PlayStation, it'll automatically read the header and set a bunch of information from that header. For example, the base offset of the exe and a whole bunch of other stuff like what CPU the PlayStation uses, so that you don't have to set those things yourself. Importantly, it also identifies symbols from the PlayStation standard libraries, but we'll get to that in a bit. With everything set up, it's time to actually create a project. Just hit File, New Project, and it'll ask you if you want a shared project or a non-shared project. Shared means you're working with a team with a bunch of different people, and that's something that I actually don't have any experience with, because Ghidra files are not files, to my knowledge, that you can just throw into like version control and have that just work. You actually have to run something called a Ghidra server in order to work with multiple people on the same project. So we're just going to ignore that for now and select non-shared project And we're just going to give our project a name and hit finish. With our project created, it's time to actually import the executable file. So we just hit import file from the file menu, and then we want the executable. These are almost always going to be on the root directory of a PS1 or PS2 or PSP game. They'll have a funny name like SLPS or SLUS or something like that, followed by a bunch of funny numbers. It'll look like that. Those are the executable files for PlayStation games. If we set up our extension correctly, we don't have to do anything for the next window that appears. The format will automatically be set as a PSX executable, and the language will be automatically set. This is the language of the CPU assembly code. So after that, we just hit OK, and then analyze, and then we don't want to uncheck or check anything here except for this aggressive instruction finder. It'll say that, oh, you shouldn't do this, this is bad or something. You can just ignore that and select it anyway. It'll identify more of the code. And after that, you can just hit analyze. And after all that, we finally have the main Ghidra window. This is what Ghidra actually looks like. So the screen is divided into all of these different sections. The important ones are this disassembly window here. That's where you guessed it, the disassembly lives, aka the assembly code. Then the decompilation window is here on the right. That's where the decompiled C code lives, actually pseudo C. And then on the bottom you have your bookmarks that you can set yourself. Automatically it'll set a whole bunch of bookmarks. You're going to want to select them all and hit delete, because none of the automatically generated bookmarks are really going to be of any use to you. Then on the left we have a bunch of stuff about data types. You can mostly ignore this one for now. Any symbols that you create later are going to appear in the symbol tree. Get to that later. And here on the top left, we're going to have the memory map, which allows you to jump to different parts of memory, like the RAM or the VRAM and whatnot. Selecting anything in the disassembly window will automatically jump the decompilation window to that same spot in the decompilation, and vice versa. Selecting this here will take you to the same spot here, and selecting this will take you to the same spot in the decompilation. You might notice that automatically some functions already have a given name, and some structs already have their members identified. That's because of the PS1 extension that we installed that automatically identified this move image function as being from the PlayStation 1 standard library, and this struct as a rectangle from that same standard library. Double-clicking a function in Ghidra will take us to the definition of that function. For example, here, if we wanted to learn more about move image, we can check it out here. We can see its parameters and the actual code that gets run in move image. Now, if we want to know what this actually did, we can check the SDK itself, because this is from the PlayStation standard library. So we can see that move image transfers data between two locations within the frame buffer, aka within VRAM. So it tells you the syntax and this explanation. And so by looking at this stuff and cross-referencing between the code and the standard library, you can understand a little bit about what code is being used where and how it works, and so on and so forth. By cross-referencing what we know from the SDK itself and what we're seeing in the code and the behavior that we're seeing in a debugging emulator, we can get a deeper understanding of what any one given piece of code is actually doing when it's using these functions. And that's a very good starting point for decompiling. Decompiling is all about taking what you know and then inferring other things from what you know so that you know more. And then with that increased knowledge, you can know even more, and so on and so forth. And we're going to get to exactly how that works in a bit. The actual act of decompiling is basically the act of assigning symbols. basically adding names to variables or memory addresses or functions, things like that. So if you have something like a variable that has an automatically generated name like local28, which means this is something that's on the stack, we can hit rename variable. And because we know how this move image function works, we know that the first parameter is a source rectangle. So we can just assign it the name source rectangle since we know that's what it is. And after assigning that, it'll appear in our symbol tree and any place in the code within the scope of this function. This variable will be identified. Now, Ghidra is not the best at identifying data types. For example, this variable here has been assigned the value 3F800000. Now, if you're a programmer, this looks very funny to you because you know that this number is actually the representation of 1.0 as a float. So we know that this number, this variable, is probably actually a float and not an integer. So what we can do is just right-click it, hit retype, select float, hit OK, and then within the code, it will appear as a float now. And guess what? That's mainly what decompilation is. You now know how it works. Congratulations. There's a lot more nuance to it, of course, but the very, very basics of it have been explained. You find pieces of code that you understand and you make inferences based on what you know so that you can identify more and more and more, so that you can have a greater high level understanding of what any given function or piece of code actually does. And after you know what it does, you can then manipulate it by using an assembler like armips to write your own assembly code to modify the game. That's how it all works. That's the big secret. Rather than going into more detail about specific features of Ghidra, let's do something real. Let's try to do an actual task with Ghidra now that we know how it works. For example, we want to modify these images. This is from a game called Blue Legend of Water, which is a game that we translated and released a patch for. Now you might be thinking, well, it's just an image. Why do we need to open Ghidra and look at game code in order to modify a single image? Replacing the graphics should be relatively easy. I have an entire video about this topic, 95-minute long video, that goes into very, very detailed specifics on how graphics can be extracted and replaced. But that's not going to apply as much to this example. In general, when you want to get graphics for extraction and editing, you look at the disk contents and you search for graphic and color palette data, and then you write an extractor and then reinsert it. There is a process and I go into all of it in this video. Not going to touch on it here, but you can watch this video if you are interested. Immediately we have a problem, because while the image appears in RAM dumps that we take of the game, it does not appear, at least we don't think it appears, in the disk files. Now, a major reason why this might be the case is because the files are compressed. So now we don't need just an image extractor and injector. We need a decompressor and a compressor for the specific compression type that the game is using. Luckily, we have a trick that we can use. Right before the graphic appears, the graphic will be sent from the disk to memory as a compressed image. Inside of memory, it will be decompressed, and then it will be sent to VRAM. We know that that has to be the trajectory of the file, so that because we know that, we can use a debugging emulator, in this case nocache PSX, to check when it's still in memory, and we can put a write breakpoint on it. That is, we make the program break or stop right when that uncompressed data is being written. And then we can rewind a little bit before that happens. In theory, the debugger should break. It should hit the breakpoint right in the middle of the decompression routine. At that point, you could just look at the disassembled code within nocache PSX and decompile it yourself from that disassembly. In fact, that's something that I've done before. And you don't technically need to use Ghidra to do that. So why do we use Ghidra? Because it makes it much, much easier to decompile that code. So here's the decompression function. And very interestingly, you can see some functions that are automatically identified. That helps a lot because that lets us know when it is that it's doing the copies from memory to VRAM. That's what load image is. It's a copy from memory to VRAM. And it also tells us that this decompression function is specific to graphics only, because why else would that be there? The only thing that gets uploaded to VRAM should be graphics. So this is what we're dealing with. This is the function that we have to decompile. And by picking apart at it, we can identify different pieces until we have the entire picture figured out. Now, we aren't just rushing into this completely blind. We should go in with some knowledge of what we think this code is actually doing to help us decompile it. For example, if we're dealing with decompression, there's a very high chance that it's using some kind of LZSS variant decompression, because that's typically what you saw in this era. Now, I won't be going into the specifics of decompression because that would make this video way too long and it could be its own video, but know that we can use our knowledge of what we already know about decompression to intuit different things about the code and be able to identify and infer different pieces of the code itself. A good way to get accustomed to how to use Ghidra and the different features that it has is to just look at its right-click menu. Now, the right-click menu is different depending on whether you're clicking on the disassembly or the decompilation. But if you just look through, you'll be able to see all the different things that you can do. For example, place bookmarks. You want to take a look at this copy special function here because they actually hide a lot of important stuff that's very useful when you're dealing with different programs. Like you have to hit copy special in order to copy an address. It's a little bit annoying, but that's how it is. There's a lot of important stuff over here on the right on the decompilation. For example, you're going to want to use this edit function signature quite a bit. What this does is lets you change which what parameters are being passed to which functions. Now, this is something that Ghidra will tend to get wrong quite often. It'll just make mistakes about the parameters, and it's up to you to manually fix them. But that's something that you get a feel for the more you use Ghidra. There's some more very, very powerful and basic tools that I want to highlight. For example, the set highlight feature, which lets you put a highlight over any variable, and which gives you a very good way to visualize if you're trying to keep track of a certain variable to see what it's doing or what it's affecting. Very, very key feature there. And now for maybe the most powerful and important feature of Ghidra, and that's the way that it automatically tracks references. For any piece of data in memory, for any memory address, it'll keep track of where that memory address is written, exactly which instruction it is, and where it gets read. That's very, very helpful for figuring out what that memory address does, because you can see exactly when it gets written to and when it gets read. And by cross-referencing those different functions that are calling it and referencing it, you can figure out what it does. And similarly for functions, you can click on any function and it'll tell you where that function gets called. For example, this function, with this automatically generated name, gets called in the main function here. It's obviously very, very powerful and very, very important for determining the relationships between different pieces of code. Disassembling is like taking apart a big, nasty plate of spaghetti. Every piece of spaghetti connects to a different piece of spaghetti, and some of that spaghetti has some sauce from some other piece of spaghetti. It's kind of a big mess like that, and it's your job to untangle it. It's really the only metaphor I can come up with. Something also very important that you hopefully won't have to deal with is the overlay manager, which is kind of a pain to get working. This will only appear if your extension supports it. Otherwise, you're going to have to do some backdoor manual way of adding overlays. Um, Overlays are basically separate executables that get loaded into memory. And in order to create it, you can use the overlay manager if your extension supports it, or you could use the memory map and map it automatically. Although in order to do that, your initial file has to actually contain that data. So you're going to have to like sandwich your executable files together and create a new one, and then have it analyze that, and then manually specify which parts belong to which addresses. It's kind of a mess, but that's currently what I have to do for PS2 overlays, and that's the only way I can get it working. So hopefully you won't have to deal with it. Now I realize a lot of this seems like I'm just glossing over a lot of stuff, and I'm really just telling you to install the program and go nuts. But that's kind of how it is. That's kind of how it is with Ghidra. Like when you're decompiling, there's really no one way to do things, and there's really no like wrong way to get information. And a lot of it comes down to just making guesses, really, of what something does, and then assigning it a name, and then hoping you're right, and then checking on it later on. So this is not so much a science as it is kind of an art. And I know some people might not like that about it. They want a much more straightforward approach to getting a certain job done. But that's really not how decompilation works, and it's really not how hacking works in general. So a lot of this, if you want to be a hacker, you kind of have to go for it yourself and try to figure it out and find out what's best for you. There are other features in Ghidra like flow graphs that I don't use too much, but it allows you to visualize the code flow in some ways. Some people like it, some people don't. What is pretty useful are call trees, because you can load up a function and then you can expand all of the functions that it calls and find this call tree. So you can see the relationships between different functions much more easily than if you were traversing this manually. For example, if you're looking for something that calls print, well, you can load up a function and then hit expand all, and it'll whoosh expand all of the functions like this. And you can see everything laid out very easily. Just what functions are being called by which functions, basically. Now, if you're like me and you have to work with a lot of text in games, Ghidra has a lot of string support, not just for ASCII, but for a lot of different text encodings that include like international text encodings, like standard Japanese encodings, SGIS. However, as of today, the main release of Ghidra does not have very good support for searching for non-ASCII strings. It kind of only knows how to search for ASCII strings. That's apparently going to change in the future with maybe the next release. So by the time you see this video, Ghidra might actually support any encoding string searching support, but currently it doesn't. Another thing you can do that's very important is set comments, obviously. Just hit the semicolon key and you can place a comment anywhere in the code. Very useful for keeping track of code and stuff. One of the most trickiest features to use is the scalar search. If you know a certain value that you're looking for example, maybe there's a cheat code that sets your health exactly to 300 and you're looking for that cheat code in the code. You could search for 300 directly and it'll pull up any instruction that uses 300 as a value directly. For example, it could be like an add instruction that uses 300. And that'll let you zero in directly on the piece of code that you're looking for. It's kind of a long shot, but it's really saved me a couple times. So it's worth just giving a shot if you have a case like that. where there's a specific number that you're looking for, and you can intuit that maybe it's just a direct instruction like that. Getting back to the image decompressor from Blue, this is what the function looks like after I've decompiled it. You can see that every symbol has an actual name attached that describes what it is, and it's now a very easy to understand piece of code, at least relatively. Now the decompression algorithm itself is pretty simple. If you want to read up on it, you can pause the video and look at this. But in these older games, it's pretty common to have a really simple decompression algorithm like this. And now that we've decompiled it, we can describe it like this. And we can also write our own version of it to use in our own tools for decompressing the files, and then later on coming up with a compression algorithm. Now, the game itself will not have the code for compressing the file, because that's something that's done on the development computers and not the PlayStation 1 that's running the game. The game itself only needs to decompress the file, so that code is not going to be provided to us even in the assembled form. So we have to come up with that ourselves. Let's try something else now. Let's try something really fun and different. This is a very, very cool game on the PS1. This is the Fist of the North Star game that's pretty infamous for having some really, really cool graphics. And the game runs at 30 FPS with a lot of frame drops. Could we get it to run at 60 by using Ghidra, even if it would only work on an emulator that supports overclocking? Well, let's give it a shot. To understand frame rate, we need to understand VSync. VSync is a function, specifically I'm talking about the way the PS1 handles VSync, where VSync is a function that causes the PS1 to wait for another V blank period. Now, if you don't know what these mean, I suggest you brush up on how a video signal is sent out from a game console, because it's kind of a little bit complicated, and there are these different like timing periods like V blank and H blank. But essentially, VSync is the function that we're looking for in the game itself to modify the frame rate. To understand how VSync works on the PS1, we can read up on it in the PS1 standard library. After reading that, we understand that what we're looking for is some place in the code where VSync is called in some sort of loop, or in some kind of case where it's being fed a variable, something like that. Luckily, by using xref, we can see exactly when VSync is called within the code. Now, there are 34 instances of it found, which is kind of a lot to go through, but we can trim anything that's from inside the standard library functions itself. So a lot of these we know aren't going to be what we're looking for this dynamic frame rate function that may or may not exist. So we can ignore those ones. By using a debug emulator and putting a breakpoint on VSync, we can figure out when it actually gets called. In this case, inside of main, there is a function, and inside that function is this VSync, where VSync is being passed a parameter, just like this. And that's kind of what we were expecting, something like this, where VSync is not being passed a static number, but a variable. So what the game is doing is it reads this memory address, which I've renamed VSync indicator, and it uses that as a parameter to feed to VSync. So in theory, all we need to do to enable 60 FPS is look at any references that write to VSync indicator a value of 2 and change it to 1. 2 means that it waits 2 V blank periods for every frame, which results in a 30 FPS on NTSC consoles. But a value of 1 results in 1 V blank instance per frame, which results in 60 FPS. There are two pieces of code that seem really promising, because we can see here that this address gets set to 2, here and here. So technically, if we change that, could be the case that we just unlock 60 FPS right from there. Let's keep going. What else can we do with Ghidra? Well, on blue, also what I had to do was remove some very terrible anti-aliasing from this game's text renderer. And I also had to replace the font entirely from the BIOS font, the font that lives in the PlayStation 1 BIOS, with a custom one. Also had to increase the text speed, but let's focus on these first two for now. The font that the game uses is really unacceptable for multiple reasons. It's a full width font, and we'll get to why that's really bad in a bit. It's horribly anti-aliased. Like you can see, it's pretty muddy looking and really blurry. That's because it's taking what is a 1-bit font and scrunching it down to a smaller size. It's really not a very good solution that they came up with. Because it's full width, it does not leave enough space for full English sentences, so there's a big problem there. And the encoding encodes 2 bytes per character instead of 1. So it means that this text, if we used English for this font, if you use this font in English, our text would take up a lot of space that would probably not fit within the original game. But the game makes it hard to replace this font because it's reading it right from the kernel. It's not in the game files. It's on the PlayStation 1 itself, the BIOS, the kernel. As an aside, let's talk a little bit about font widths. So I said that full width was bad, and that's because each character is uniformly spaced and spread out, and it's generally quite wide. You can see that this text right here looks really bad. This is a full width font. Now, we could convert that to a half-width font if we could control the game's code pretty easily. Each character still takes up the same amount of space, but is not as widely separated. The kerning is much, much better on a half-width font, especially if we could control the font itself and add some details to it that makes it look better. For example, the serifs on this I gives it a lot more width, so that it doesn't look so out of place. For example, this I doesn't have those serifs, so it looks super thin, and it creates a lot of empty space. The best kind of font is a variable width font. This is what I did for Boku no Natsuyasumi 2, is I implemented a variable width font, but that takes more work and is not always necessary for a very low resolution game like a PS1 game. Because the game is using the BIOS font, we can figure out exactly which piece of code is rendering the font. And we do that because we have read through the PS1 standard library, and we know that there's a specific function that's used to get the address of characters in that font from the BIOS. It's called krom2rawadd, which is quite a mouthful. I don't know why it has this very long name. But we know that how it works is we give it the encoded SGIS character, and it gives us an address in the kernel of the character of the font. From there, it's very easy to trace within the code where the text rendering function is, because a function will, in theory, call this krom2rawadd, and then it will perform some sort of memory to VRAM copy, where it copies first from the BIOS to memory, and then it uploads that character from memory into VRAM. And if we can control that mechanism, we can control what the font looks like. And by doing that, by tracing it, we look at krom2rawadd, and we can see which function is calling it, and we can find it right there. And that's exactly how it's calling that function. If we want to replace a font, we obviously have to load that new font into the game somehow. And by analyzing how the BIOS font works as a graphic, we can create our own font and convert it to the format that the game is expecting already, or the BIOS font. That way it makes it a lot easier to write our new text rendering function. Now that we know where the function is, we can replace it with our own function that we write in assembly. I used armips to write this assembly. Armips is an assembler for ARM and MIPS, as the name would imply. The PS1 uses a MIPS processor, and so it supports the PS1. What's interesting about Ghidra is after we have created an assembly patch, we can reanalyze the file in Ghidra. We can load it up and analyze it again. So we can see the C decompilation of the code that we wrote ourselves. And by doing that, we can easily check if the code we wrote is doing what we think it should be doing. So that's a very, very interesting use case of Ghidra, is to analyze code that you've written yourself. And there you have it. Here's how the game looks with this new font added to it and having it rendered by our new renderer. So we can fit more characters per line, and we have changed the encoding entirely. We don't use 2-byte characters anymore. We just use single-byte characters, and it's much more narrow and nice looking without any of that anti-aliasing. Ghidra is cool because it lets you dig up all sorts of weird stuff. For example, there's a game that may or may not be coming in the future that uses something called the I mode. Now, the I mode was a way of connecting your cell phone to your PlayStation. Yeah, they had that in Japan. Not a lot of games supported it, but the ones that do often hid a bunch of exclusive content behind this I mode and have essentially been lost forever. Well, by doing some digging in Ghidra, you can actually find those assets and reinstate them in the game. Keep an eye out for that. That may be coming in the future from a project that I'm working on. Now, the biggest project that I've worked on involving Ghidra is Boku no Natsuyasumi 2. I had to do a lot of work within Ghidra on this game. I had to completely rewrite this text renderer, which is much more difficult on PS2 than PS1 because the tools are not as good on PS2 versus PS1, including replacing this vertical text with horizontal text. I had to completely reverse engineer the game's scripting system in order to add subtitles to scenes that didn't have subtitles. Besides that, the game didn't allow you to edit any of the files at all and would actually just crash itself if you tried to edit anything. So that was an anti-tamper mechanism that I had to disable. And that I did that through using Ghidra. And much, much more that I'll be explaining in a future video. There is a lot of work that had to go into the Boku no Natsuyasumi 2 patch on a technical front. Check that out when that video drops. But that's all for now. There is so much more to Ghidra that I haven't explored here and that I haven't even explored myself. But it is a very, very powerful tool. Like I've explained, even without getting too familiar with it, you can start really digging and doing work with it and really accomplishing tasks. It's powerful, but it's also very lightweight and easy to get going with it, which is one of its big strengths compared to other programs. And if I didn't mention it before, it's completely free. Yeah, Ghidra is a product of the United States National Security Agency, which you might feel a certain ways about that, but it's really good. They did us a solid for once. That's Ghidra, and if you have any comments or questions, I'd like to hear about them. I know this video couldn't cover everything, but I wanted to just give a basic overview of what Ghidra does and how it can be useful so that maybe you're interested in learning more about it. So thanks for watching, and I'll see you in the next one.